So far we've talked about, well, technically three laws of thermodynamics because we talked about the zeroth law. But the first law, which has to do with energy conservation, and the second law, which is, at least the way that we phrased it, a very qualitative statement that heat spontaneously flows from hot to cold, but not cold to hot. And when we talked about and solved problems with the first law, they generally took place on PV diagrams, whereas so far we've just kind of discussed the second laws in a conceptual framework. So all of that stuff comes together in the form of heat engines. So this is a heat engine, and what it's going to do is it's going to capture and convert to work some spontaneous heat flow from hot to cold. So here I have an alcohol lamp. Here's a piston, which is being heated up, the gas inside the piston. And it's going to want to go towards the colder side, so there are baffles here to vent the heat. And here's a colder piston. And as the pistons reciprocate to let the hot gas and cold gas exchange, these flywheels and pistons are going to take advantage of that, I hope. So, ta-da! Behold the wonders of industrialization. So this is not really a thing that we're going to analyze on a mechanical level, like forces, for instance. We'll use PV diagrams, and then we'll also describe it in terms of things like efficiency. That's, by the way, what's called a Stirling engine. And at some point, I probably will draw the Stirling cycle. So here we have, our first statement, at least, of the second law of thermodynamics. Heat spontaneously flows from hot to cold, never from cold to hot. And then we have this idea that we can capture some of it and convert it to work. This is the type of diagram we'll use to explain that process. So here's heat flow, Q hot, from what's called a hot reservoir. So this would be, the piston heated up by the alcohol lamp. And then it's going to want to flow to the cold reservoir naturally, and we just dump an engine in front of it and convert some to work. So details missing. So the first thing we have is the first law of thermodynamics, which is, again, kind of a glorified version of energy conservation. And now that we have two Qs, we got to worry about the signs of this one as well. So the arrows tell you the story. So I've got an engine. I'm withdrawing Q hot from the hot reservoir, and that equals W plus QC. So again, the arrows will tell you I've got Q hot flowing in, and then it splits and divides into the waste heat, QC, and the work. So this is kind of the master equation for engine, a cycled engine. So the next thing we can do is we can start asking about the efficiency of an engine. And usually that's given this kind of lowercase e of some type. It might be a lowercase e. I think in your textbook it's one of these squiggly epsilon e's. And this is a definition. We'll just define this as the ratio of work, useful work, to the amount of heat that you withdraw from the hot reservoir. So let's say that you, for instance, pull 100 joules out of the hot reservoir, 100 joules of heat energy. You convert it all to work. So that's 100 joules, that's 100 joules. That would be efficiency 1, or the maximum efficiency. So with this statement of energy conservation, we can phrase this in a couple of different ways, which may or may not be useful. So we could phrase work as Q hot minus QC. Or we could factor and simplify this way. So these are all equivalent statements. So that's the efficiency. So for instance, I could draw two engines that are just completely ridiculous at the asymptotes. And in fact, one of these will be impossible. So as I do this, you should determine the efficiency of each. And it shouldn't take any serious calculation. So engine 1 is we convert every single joule of heat energy to work, and probably much more reasonable is engine 2 that broke. So this would be an efficiency 1 engine. So work and QH are the same. All 1,000 joules that go in get turned into work. And implicitly, this is what's happening every single cycle of the engine. So these are cyclical processes, and we'll get to that when we get to that. So in this case, we have QH equal W, so that would be perfectly efficient. And in this case, we're doing no work whatsoever, so this would be an efficiency 0 engine. These are as good or as bad as you can get. When we talk about coefficients of performance for refrigerators, they're not bounded by 0 and 1, unfortunately. So it's less of a useful, less of an easy definition to use. But for engine efficiency, 0 to 1, max and min. Okay, so let's just put up some numbers so you can map this onto some semblance of reality. And automobile engines are probably about 20% efficient. So really just jump right into the deep end of the pool with units. Never ever talked about horsepower, and even the efficiency, that's kind of a curveball because we've never talked about efficiency actually ever, but we were given these unitless 0 to 1, and now we're 20% efficient, whatever that means. So when in doubt, maybe draw this picture again. So I've got T hot, I've got my engine, which I'm going to stop calling E for engine, and I've got the cold reservoir. So first task is map this onto like what's actually going on in a real process. So maybe it's worth pausing and asking yourself, what is all of this? Like, what are these parts? Clearly, the engine is the engine. What is the hot reservoir? So the hot reservoir is the burning mixture of gasoline vapor and air inside of the pistons. So this is, when you have like a 2.5 liter engine, this is the amount of volume that you can actually squirt the gas into and ignite it. And then what is T cold? T cold would be basically like the atmospheric temperature. It's more likely the temperature of your exhaust system, but atmosphere inside of the engine itself, useful work. Right? And then these all have SI units of joules, so we can equate those like we did before. Okay, so first issue is that we were given the efficiency not in the way we expected it, just units-wise. 20% efficient would correspond to an efficiency of 0.2. The definition, work in Q hot, we're asked for how much heat is required, so that is Q hot, and then we're told this. Basically, they don't try to sell you a car by telling you how much waste heat it generates. The 250 horsepower is the useful work. It's just in funny units, so unit issue number 2. Okay, so got the 0.2, we want that. Really just need to find work. What is horsepower? And if you look it up, 1 horsepower turns out not to be something in joules, it turns out to be something in watts. So we have our 1 hour time period, so we would turn this into the amount of joules that the car turns into useful work over the course of 1 hour by taking Okay, 250 horsepower times this many watts per horsepower times 60 times 60 seconds per hour. So dot, 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 unit conversion. And the unit conversion is as such. So we have 250 horsepower. We have 745.7 watts per horsepower. And then that will leave us with joules per second. So we got to multiply this by the number of seconds. So that's 60 minutes in an hour, 60 seconds in a minute. So this many seconds would give us joules. And so that math happens, and we end up with so just about 1,000,000 watts times 3,600 seconds. So this is a reasonably large number. I'll just leave it there. This is the amount of energy. And this is the work. So this is the number of joules that your car, operating pedal all the way down would do over the course of 1 hour. Right? So the rest is just a little bit of arithmetic because we know this thing is 20% efficient. So for instance, if we have 100 joules of heat from the burning of the gasoline air mixture, then we would only get 20 joules out of useful work. So finally what I get is I should be less casual about that because we got W for watts floating around. So this is the useful work, and that's like 3.7 gigajoules. I mean, I know it's got like a dirty reputation, but like from a physics standpoint, gasoline actually really is amazing. I think I kind of calculated it once that your entire energy requirements as a human being for a month is like less than a gallon of gas if you could digest gas. Okay. But anyway, run your car, pedal all the way down for an hour, 3.4 gigajoules, which means that the efficiency being 0.2 would let you figure out how much waste heat or how much heat it required to do that, and therefore the leftover is waste heat. So efficiency 0.2, we got our work. This tells me that Q hot is equal to oops, sorry, I already did that. Let me fill in that number in 1 second. Yeah. 680 million joules. Got that wrong. This is the 3.4. Gigajoules. And we'll write it like gigajoules because that looks nice. So that's definition of efficiency. Second question is how much waste heat does this generate? So this picture is always really helpful. Energy conservation is always really helpful. What energy conservation tells me is that QH equals QC plus W, and this is 3.4 times 10 to the 9. QC is what we want, and then this is 6.8 times 10 to the 8 joules and joules. So we should get like 2.7 or something. Yeah, 2.7 times 10 to the 9 joules. Right. So again, implicit in this is all of the signs and the idea of energy conservation. So it's a really useful picture. Okay, so this is how much energy you produce by burning the gasoline. This much is what you just like throw into the atmosphere in the form of heat. Okay. Yeah, and just scribbled also in the margin of the notes, there's note that this is enough energy to melt 8,000 kilograms of ice. So if you wanted to know that. So it's quite a lot of heat. Okay. So those are all the moving parts. Now what we want to do is actually look inside of particular cycles. And we're going to use, again, PV diagrams to do it because they basically tell us everything we need to know about the cycles. All of these, to some degree, are idealized. You'll never get a pure isotherm or isobar or adiabat, but we try. And we'll answer two types of questions, some practical and some, scientific. So first question is, can you get to the maximum efficiency? Could you get something that actually has E equals 1? And in a picture, again, E equals 1 would be this. I withdraw some amount of energy from the hot reservoir, and I turn it perfectly into work. And there's absolutely no energy wasted and waste heat dumped into the environment. So as a practical matter that we don't do this, otherwise we would have these machines. But it turns out as a purely like scientific theoretical construct, you also cannot do this. And this is another statement of the second law of thermodynamics that basically just says like, no, right? So what I'll do, and the proof of this gets a little bit into the weeds. It's actually a really cool proof, and if somebody asks me, I'm happy to tell you. But we'll just say the so-called Carnot cycle can be proven to be the maximum efficiency cycle. And the proof of it is based on the fact that it's reversible, is that you can actually operate it forwards and backwards. And the Carnot cycle PV diagram looks like this. We have two adiabats and two isotherms. So the isotherm legs I'll put in red because that seems like an isotherm. So we have an isotherm from A to B. Isotherm means same temperature, so we can just label the temperature. This is going to be above that, so we'll call it hot. Seems good enough for me. And we'll call this cold, T cold. So the really nice thing about the Carnot cycle, in addition to being the maximum efficiency cycle, is that it actually kind of makes sense from a practical standpoint. Is that I have a hot and a cold reservoir. Look, there they are. And then I have two adiabats, which if you remember mean no heat. The temperature might change, but the heat does not flow. Heat does not flow into or out of the system during an adiabat. So this is an adiabat and that's an adiabat. So from B to C and D to A. And as well as the goofy name and the fact that we haven't talked about it a lot, like adiabats might seem kind of mysterious, but they're actually really not. Adiabat means no heat flows. So that really just means like it's isolated. So you put the whole thing in a really good picnic cooler or a really thick metal engine. So weirdly, the Carnot cycle, as well as again being a nice theoretical construct, it's kind of like a sensible and practical thing to visualize. I've got hot and cold, and then I've got a machine that doesn't really let a lot of heat flow out of the walls of the engine. So from A to B and C to D, we have isotherms. And isotherms are categorized by, they're defined as temperature as constant, but we know that means that the change in internal energy of the gas is also equal to 0. So as a consequence of that, in the first law of thermodynamics, which is very useful. Okay. So really an adiabatic process means like super slow. We'll kind of skip the discussion of quasi-static. We'll just say that you're insulated in a big container, right? So you don't have any net heat flowing into or out of the thing. Okay. So it turns out that you can do a bit of work, and you can, again, prove that the Carnot efficiency is the maximum efficiency. And probably in more recent years, you'll find this in a lot of books as like ideal, like this is the best you're going to get, sure. And you can calculate that the Carnot efficiency so this is every efficiency. But what you can calculate for these cool isotherms and adiabats, so the adiabats have no heat flow, and the isotherms, you can equate the heat flow to the temperature. So that's not a proof, that's just a statement of how the proof would proceed. The really neat thing is that you could do this with work too, and you would get a whole bunch of like weird natural logs and they would vanish. But anyway. Okay, this is more important than it seems at first glance. So this not only tells you the maximum efficiency that it doesn't only tell you the efficiency of the Carnot cycle, which is kind of a sensible thing to visualize. It also tells you the maximum efficiency of any engine possible, right? You cannot exceed this. So now you guys can go to work at the patent office and he approaches you with an engine design. You don't have to pick into the details of the engine design. All you have to do is squint at it and say, okay, is your claim better than this? If it is, know that your machine's not gonna work. So this is an inviolable law of physics. So in some sense, this is also the second law of thermodynamics. And there are, again, 3 ways of phrasing it that I know of offhand. And in essence, this is one of them, right? This is another one, and our first one was another one. Okay, so let's say that we want to get this 20% efficiency. So let's see how our car stacks up. Okay. So let's see how good your car did. And there's as usual, like kind of a sneaky surprise in this, or an attempt to trick you, I suppose. So we have our car's efficiency, so let's calculate the maximum efficiency, which would be the Carnot efficiency, which would be 1 over Tc minus Th, 1 over cold minus hot. So the question is, what's the cold reservoir? Again, when we spit out exhaust, we spit it to the atmosphere. So I'll just call that 20 degrees Celsius. And yeah, it should be true that, if the temperature goes down, all other things equal, you should have a more efficient engine. And I'll do that, and of course I've made a terrible mistake. And you guys know what it is at this point. So we got away with it a lot of times, but not so much here, is that this is the delta T, and this one's really insidious, but this is not. So you absolutely cannot use Celsius here. So absolutely not. So really this is Kelvin only. So we have 1 over 20 plus 273, so we'll just call it 293.15, gotta be Kelvin, divided by 300 plus 273, which is 573.15 Kelvin. And that really changes the efficiency a lot. So I think this gets you to 0.93. So max efficiency would be 93%. Our car is 25% or 20%. We definitely have a long way to go. Okay. So this is really it, to be honest. You have 2 ways of analyzing thermodynamic devices. You can ask a first law and a second law question. So you can ask, did you violate the second law of thermodynamics? And the way that we have to analyze with numbers now is through the Carnot efficiency. And then you can ask a first law of thermodynamics question, which is, did you violate energy conservation? And if it violates any one of those 2 things, first or second law, then you know the engine won't work. So really quickly, I'll put up the other, or label this. So this is really a statement of the second law of thermodynamics. So this is what's called the Kelvin-Planck statement. Which is that. And then we also have the Clausius statement. And all of these are the second law of thermodynamics. So this is basically what we started with, is that heat does not spontaneously flow from cold to hot. And then our second version is that you cannot beat the Carnot efficiency. So this is the maximum efficiency that you're allowed to achieve. Okay. And yeah, there are actually even more. So last topic, this isn't anything new. All that we've done is done some relabeling, so you don't actually need to, invoke any new physics to talk about refrigerators. All you have to do is realize that people have decided that efficiency for refrigerators is, I don't even know if it's that awkward. People just don't talk about the efficiency of refrigerators. They talk about the coefficient of performance. But let's analyze refrigerators, and basically you do all of the same thing with one quirky definition. So what is it that you want to do with a refrigerator? You want to pull energy out of the cold reservoir, right? And it's not going to happen spontaneously. So what you have to do is you've got to put an engine there, and you've got to put work into the engine. So basically, this is a heat engine. I've just flipped all the arrows. And literally, if you write a PV diagram, draw a PV diagram for one of these devices, you just literally take an engine and you circle it. Instead of one way in the PV diagram, you circulate it in the opposite direction. So in some sense, the Clausius statement says there's no such thing as a perfect refrigerator, i.e. work has got to be greater than 0. So that's the second law of thermodynamics. But you probably knew that. And the only difference, again, is that we're going to define a thing called the coefficient of performance. And it doesn't have a cool little single letter acronym, I think like COP or something as usual. So this is, again, what you kind of want to do is you want to get the most amount of cold heat flowing out of your cold reservoir and put in the smallest amount of work. So the more heat, the less work, the better your refrigerator. So this is the coefficient of performance. And you can do the same thing with the first law of thermodynamics. Note that work is, again, equal to Q hot minus QC. The diagram tells you that's true, is that this plus this equals that. So that equals that minus that. And you can, again, simplify. So all of these are the same thing. So this is a set of 3 possible different definitions. Okay, so let's just do a problem with that and see how we do. And then in lecture, we'll do the patent office roundup where you guys get to debunk various claimed machines, either with their energy conservation issues or their entropy or reversibility or efficiency issues. Okay, so I get a nice new refrigerator out of the box. It's got a coefficient of performance of 3. It draws 250 watts of power. And I plug it in at room temperature. Let's call room temperature 300 degrees Kelvin. And let's say operating temperature is about 280 degrees Kelvin. Seems reasonable. And of course, we'll say nitrogen is N2. Okay. So we start with room temperature air inside of it. It's a pretty big fridge, like 1.5 meters cubed is fairly appreciable, so that's full-sized. And I want to know how long it takes and how much waste heat it expels. So this involves a little bit of everything, because we've got to go back and talk about how much energy it actually takes to take 1.5 meters cubed of nitrogen and get it from that temperature to that temperature. So this is the part of thermo where you get in trouble if you compartmentalize too much, is, I do have to figure out how much energy went into or got pulled out of the nitrogen. So QC is the energy lost by air. And I can figure that out in the usual way, Cm delta T, where this would be the specific heat of nitrogen. I think this is a constant volume process because this is at a constant volume. And probably if the refrigerator was airtight, the pressure would drop a little bit. So technically what this is CV, constant volume specific heat of nitrogen. Okay, so I'll go a little bit fast because we did this a few times. So this is the constant volume specific heat of nitrogen. I can either look it up or figure it out. I get it in kilojoules per kilogram K. I like all of those repeated letters. That's kind of cool. So if I chose kilogram or kilojoules, I got to keep kilojoules. Okay, I will look up the mass density of air, because I have kilograms down there. That's got to be kilograms, 1.225 kilograms per meter cubed. I have 1.3 meters cubed of it. And then delta T, doesn't matter if we have Kelvin or Celsius, they're all the same. We're dropping it by 20K. And that turns out to be 26.4 kilojoules. Making sure all my units check out, that's good. Okay. So that's how much I've withdrawn from the cold reservoir, how much I need to pull out to get my fridge to whatever operating temperature that is, 26.4 kilojoules. I know my coefficient of performance is 3, so that would let me find the work that I would need to do that. And I could go right to waste heat if I wanted to, but I'll just figure out the work along the way. So I have a COP of 3. That's equal to 26.4 kilojoules per kilojoules. And then work. So the work would be a third of that. So 8.8 kilojoules. And then I can use energy conservation, finally, to get the waste heat. So the waste heat would be making sure I'm doing good with signs. So I have QH equals QC plus W. So 34, something 35.2. Great. So those are all the heats. So we had to put 8.8 kilojoules in to moving 26.4 kilojoules out, and then it all turned into 35.2 kilojoules of so-called waste heat. Okay, how long does this take? Well, so how long does it take is just converting this. So we have 250 watts at our disposal to do that. So the question is what is that the energy of? Should I use that energy to figure out the time, or that, or that? So it will be the mechanical work. So we did need the mechanical work. We couldn't have taken that shortcut and gone right to QH. So 250 watts is 250 joules per second. And that would be equal to the total amount of joules we needed, which is 8,800 joules over t seconds. And then math happens, and we get the time it takes to do this is 352 seconds. And that's about 6 minutes. Okay. So again, no new skills. It's really just first law energy conservation, second law efficiency. And we really haven't finished talking about the second law yet. But there's a different definition, and flip all the arrows, for a refrigerator versus a heat engine.